Welcome students. We want to discuss about applications of double integral in this lecture. We'll be discussing very few applications and mostly the traditional ones coming from physics and say population dynamics and so on and so forth. But the current application is much beyond this. You can look at the application of double integrals or just integrals, for example, double, triple, n integrals in data sciences as well. You can, so let's start with our mass of lamina example. So recall, first of all, so what does density mean? Density is, density is given by, density mean amount per unit space. That is what the meaning of density is. So, so we want to solve the following problem. Define the mass of the lamina that occupies the bounded region R with continuous function delta xy, continuous density function delta xy, and that mass is given by m, which is double integral of delta x y dA, where this double integral is over region R. So what is happening? So the idea is you are given a lamina. So lamina can be thought of as a thin sheet of metal, or so it's a very thin sheet. So essentially, and the density at every point is different. So say density at this point, if this point was xy, density at this point is given by delta xy. Yeah. So this is a point x comma y, and the function defined on here is delta xy. So roughly your delta xy is essentially limit as delta m over delta a. Yeah? So that's how you basically compute the compute the density. All right. So suppose now we have other way around problem. So what is this limit over? The limit is basically over all the disk getting smaller and smaller which contain xy. Yeah. So we are given at each point, we are given delta x, y, and which is the density, and we want to find out the mass, right? So, so if you look at this, mass is going to be, so what we do is let's take a rectangle. So you divide your domain R. Now note the domain is same as the space occupied by the lamina, and you approximate it by rectangles. And now for each rectangle, so we have all these rectangles, division of lamina. Now for each rectangle, we'll have a point inside. We can approximate it by, take a random point inside that rectangle. We can approximate our mass by xi star, yi star times delta x delta y. So this is approximation because mass is, so from here you should get delta A times delta xy is roughly equal to delta m, right? So this is the mass of lamina in this rectangle here. Now you take the sum, say if you divide it, the number of rectangle divisions are say m here and say n here. Now I don't want to use same m, so let me call it different. So there are say L here and k of these, then we get summation I going from 1 to L, summation J going from 1 to K. This is a rough approximation for your area, and if you take the limit, you get the following. So when you take limit, you get the actual mass, limit K L going to infinity, summation J going from 1 to K, summation I going from 1 to L, delta X star Yij star dA, which is same as delta X delta Y, right? So let's just write that for delta A. Yeah. So this gives us basically the thing. Okay. Now, one example for it here is you're given at each point, you're given the population density, right? So this is your Vancouver region. Suppose you want to define your, this whole thing is your Vancouver region. Let's call this D, then the population of Vancouver, because you're given population density. So population of Vancouver is going to be integral over this region D, which is essentially the Vancouver, area of the Vancouver times delta xy dA. Yeah, and so you'll say, well, here there's an approximation again already. So each point, say for example, over 10,000, they are marked here. So you will basically compute. So if you have to compute this value here, you would actually use the double Riemann sum as an appropriate approximation for the for the um, for the population of Vancouver. All right. So this is about the mass of the lamina, right? This is the definition of mass of the lamina, and this is a justification why such a definition is a meaningful definition. Now let's discuss the next thing, which is called the center of mass or the centroid. So what is the center of mass? Center of mass essentially is a point in which you can think that your mass is concentrated. Yeah. The idea is, I suppose you have this lamina here, and this is a point on which if you put a needle like that, you can balance this whole object, which is a what? Which is a weird shaped object, but if you put the needle here, it will balance on it as if the mass was concentrated there. So such a thing is called center of mass. So the coordinate of the center of mass is given by x bar, y bar, where x bar is 1 by m integral of delta x y x dA, and y bar is 1 by m double integral of y delta x y over region R. So if you basically the whole lamina basically behaves as if the entire mass is concentrated on the center of mass, right? So if you want to balance the lamina, you can just have kind of needle balancing this, and the whole lamina will balance out horizontally. So these are the formulas for the center of mass. Note that these are generalizations of the usual uh, definition of center of mass, except this is in an integral format, right? So now let's look at the following problem. So find the center of mass of a particle lamina that of a plane lamina that occupies a region bounded by x equals to 0, y equals to x squared, and with the density delta xy. Okay. So first of all, let's draw this region. So 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 y equals to 0. So y equals to 0 is x-axis, and y equals to 4 minus x squared is the inverted parabola. So let's draw the inverted parabola. So this is how your region looks like. This is your region R. This point intersection. So you need to find out these 2 points of intersections. So for that you have 4 minus x squared equals to 0 gives me x equals to plus or minus 2. So what is our mass going to be? So mass is double integral over region R of delta xy dA. Now we can write it as iterated integral. So this is, it'll be easier to take it as y first region. So y, when you have an arrow in this direction, it hits this curve first, which is y equals to 0. And when it leaves, it hits 4 minus x squared. Your x ranges from -2 to 2. And your density delta xy, which is y, you have dy dx. So this integral is going to be y squared by 2, 0 to 4 minus x squared, minus 2 to 2 dx. We can bring 1 by 2 out. We have minus 2 to 2, 4 minus x squared, the whole square dx. Now this is an even function, so you'll get 2 times that. So we have 1 by 2 times 2, 0 to 2, 4 minus x squared, the whole square. Let me expand that. So 16 plus x to the 4 minus 2 times 4 times x squared, which is 8x squared dx. Now this is going to be 16x plus x to the 5 over 5 minus 8 x cubed by 3, 0 to 2. So the answer is going to be 16 times 2 plus 2 to the 5 by 5 minus 8 times 8 divided by 3. And you can simplify that answer. So let's talk about moment of inertia. So moment of inertia is given by the following. We have, oh, sorry. So we had to also compute the center of mass of this lamina, right? So this is going to be 256 by 15. So this is the mass M. So now we need to compute the center of mass. So the center of mass is given by 1 by M x times delta xy dA. Yeah. So note that center of mass is also called moment. So this x bar is also called moment of lamina. This is called moment of lamina. Similarly, y bar is called moment of lamina. in X, and these are essentially called first moment. So we are computing now the X bar and Y bar for the center of mass here. So X bar is going to be integral over region R, Y, delta XY dA, which is integral again 0 to 4 minus x squared minus 2 to 2 and y times delta y. So we get y square delta y, sorry, dy dx. So similarly, we get y bar is integral over r. So I'm going to write down the region now directly, minus 2 to 2, 0 to 4 minus x squared x, y. My apologies, this should have been dy dx. Now this could be broken. So let's compute these integrals now. So in this case, we have y to the power 3 divided by 3, 0 to 4 minus x squared minus 2 to 2 dx, which is minus 2 to 2, 4 minus x squared whole cube divided by 3 dx. And once you integrate this, you will find the answer is 4096 divided by 105. So this was your x bar. What we are missing in writing x bar is the factor of 1 by m here. Let's write down 1 by m. Again, 1 by m here. 1 by m. This divided by, so dividing by 256, so multiplying by the reciprocal. So 256 divided by 15, and that turns out to be, this turns out to be 16 over 7. Similarly, I have 1 by m here. This is going to be 1 by m. Now we integrate this guy, so we have minus 2 to 2 x times y squared by 2. That's the integration of y. So we have y squared by 2. We have 4 minus x squared, the whole square divided by 2 dx. And now the nice thing about this is that this function inside is an odd function, right? And you're integrating that function from minus 2 to 2. So the answer is going to be what? 0. So therefore, x bar, y bar equals to. So first one is 16 by 7 and y equals to 0. So this is your computation of center of mass of plane lamina and also the mass of it, right? So we started with mass and then we found out center of mass. Now we want to talk about the moment of inertia or the second moment. Yeah, this was the first moment, right? So the first moment is here x times delta xy. Second moment would be what? X square. Third moment will be x cube and so on and so forth. They have significance in the setup. So let's consider the following. Second moment. Let R be the plane lamina and L be a straight line that may or may not lie in XY plane. So you have your lamina, which is given by region R, and you have a straight line which may or may not lie in the plane. I'm drawing it here. Now, the moment of inertia of R about axis L is defined by, so at every point you are looking at the distance of, so you're looking at this distance d, or in this case it's omega w. So this is, if this is xy, this perpendicular distance is wxy. And the second moment is basically given by, again, density as it is, you multiply by square over region R. Yeah, so there's a variable density variable distance w at each point, right? So you have the distance squared from the axis of rotation. Shouldn't call it rotation at the moment, but it's from the axis to the point times the density times dA, and you compute the integral of this. All right. So what does it really captures? So density is usually, so the second moment essentially captures the the quantity that the effort required to spin the object around that axis, right? So there are a few special cases when L is an x-axis. So if we take R, if we take L to be x-axis, then if we look at point xy, this distance is going to be y, right? So instead of omega, or sorry, w, you would have w of xy is y in this case, when your L is x-axis. So that's why you see, if L is the x-axis, then Ix is given by double integral y square delta xy dA over region R. Similarly, now you can have L is z-axis, then it's given by x square delta xy dA. Now, suppose if L is z-axis, so suppose you have, again, you're thinking about this. Note that you're thinking about lamina as a thin sheet, a very thin sheet, right? So you're not associating volume with this object, right? You're only associating area with this object. So then you're looking at this distance, and this distance is going to be distance from the distance of this point xy from the origin, right? And that distance is given by square root of x square plus y square is your omega xy, in case you have what L is z-axis. So you see all this, then all these results are justified. So the one around z-axis is called I0, along y-axis called IY, along x-axis called IX. Now I0 is called the polar moment of inertia because it's around origin. All right. Okay. So let's look at the following problem. A lamina occupies the region R in the plane that is bounded by parabolas x equals to 1, y equals to 1. And density of the lamina is given by delta xy, which is x square y. Find the moment of inertia of lamina about the x-axis and y-axis. So let's first draw this region R. So x equals to 2 is going to be here. Let's draw it with a ruler. So x equals to 2. Use a different color pen. X equals to 2. Then we have y equals to 1. So I'm going to do some rescaling here. So this is our x-axis, this is the y-axis. This is your y equals to 1. We have x equals to 2. And the other one is a parabola, y equals to x squared, which basically is, and since we are only interested in this part of parabolas, 1, 2. So this is our region we are interested in. So this point is going to be 1, 1. And this point is x is 2, y is 1. And this point is going to be intersection of parabola and this line. So it's going to be 2, 4. Okay. So now what we want is, so density is given by this. Find the moment of inertia about x-axis and y-axis. So about x-axis is given by, so let me just mark this curve as well, y equals to x squared. So about x-axis, it's given by integral over this region R. Let's call this region R. So let's call this Ix. Ix is y squared delta xy dA. Now that is going to be y squared times x squared y. Now in this case, again, we can go y first. So y first dx. Only thing to note is that your y is changing from 1 to x squared and your x is changing from 1 to 2. So this integral is now 1 to x squared y cube x squared dy dx 1 to 2. So this is what your Ix is, the moment about x-axis. So let's compute this integral now. So this is going to be y to the power 4 over 4, 1 to x squared, 1 to 2 of dx. This is 1 to 2 of x to the power 8 minus 1, 1 by 4 outside dx. And now we can integrate the inside part, which is going to be, so we have here x squared and then there will be another x squared here. So then this integral turns out to be 1 by 4. Integral of x to the 10 is x to the 11 by 11 minus x squared, so x cubed by 3, 1 to 2. And if you do this computation side, it turns out to be 1516 over 33. Okay. Similarly, what is your Iy? So in moment of inertia around y-axis is essentially, again, the region remains the same. it will be x square times the density function, which is x square y dy dx. And in this case, we have so this is going to be integration of y is, so we have x to the 4 already, we have y squared by 2, 1 to x squared 2 dx, and that is going to be 1 to 2 of x to the 4 times x to the 4, take 1 by 2 outside, minus 1 dx. And when we compute this integral, this turns out to be 1138 by 45. So these are your moment of inertia around x-axis and y-axis. All right, so next application, in fact, quite interesting application, is seeing probability as the integral. So recall, if you're given the probability density function of f of a continuous random variable x, what does this probability density function satisfies? This probability density function satisfies f of x is greater than or equal to 0. And if you integrate from minus infinity to infinity f of x, you get 1, right? Okay, so this is a probability density function. So probability that x lies, the value of random variable x lies between a and b is given by probability that your x lies between a and b, and is given by integral a to b fx dx. So this is what the probability density function is for random variable x. Now suppose you have two random variables x and y, then we need to talk about the joint probability density function. So the joint probability density function is of a pair of continuous variable x and y is a function f of xy again, so that f of xy is greater than or equal to 0 still. And what you have is minus infinity to infinity of f of xy dA or dx dy, if you want to write, should be equal to 1. So this is what a joint density function is. Now suppose you want to find out the probability that your xy lies in region D, then you can get that by probability that xy lies in D is the double integral of f of xy over dA of this thing. Okay. Similarly, so this gives, so you can see the idea of density function here corresponding to probability density function. And then this integral should remind you of what? Remind of mass. The first moment are also so-called the expected values of x and y. Okay. And the second basically moment gives you the variance and so on and so forth. Okay. So let's so if x and y are random variables with joint probability density function f, then we can define so-called x mean and y mean, and x mean and y mean is given by mu1 is x times f of xy r square, or r square, which is you're integrating over whole plane, and mu2 is given by this. Yeah. Another interesting thing I would like to point out is probability that your x, random variable x, lies between a to b, and your y lies between c and d, is integral a to b, integral c to d, f of xy. This is your joint density function. Dy dx. Okay, so let's look at the following problem. If the joint density function for two random variables x and y is given by f of xy equals to c times x plus 2y, if your x is between 0 and 10 and your y is between 0 and 10 and 0 otherwise, find the value of c. Problem 1. Problem 2, compute this probability that x is less than or equal to 7 and y is greater than or equal to 2. So if you look at this problem, you're given a joint density function and you need to find out what this value of c is. Well, so what is the property of joint density function we know? The property of joint density function we know is that if we integrate minus infinity to infinity, so if we integrate it over R2, xy dx dy, let's say, this is going to be 1, right? This is the property of joint density function. So we get minus infinity to infinity, minus infinity to infinity, f of xy dy. Now, but note that your function is 0 outside this rectangle. So now I can restrict myself to this rectangle. So it's going to be 0 to 10, 0 to 10, c x plus 2y dy dx. I chose y first because it's a rectangle. It wouldn't make a difference, and also there's no difficulty in computing the integral. So this is going to be c comes out. This is going to be, so y first, so 0 to 10 we have, so we get, so c is out. Now we integration with respect to y, so this is going to be xy plus y square integral 0 to 10 for y, sorry, limits are 0 to y for 0 to 10 for y, so an integration of this, and this is going to be c times 0 to 10 of 10x plus 100 and dy, and the answer turns out to be c times 1500. So therefore c equals to, so c times 1500 is 1, so c is 1 by 1500. Okay, so now we can work this out. So this is equal to, so what is the probability that x is less than or equal to 7, y is greater than or equal to 2, is essentially your x is less than or equal to 7, so minus infinity to 7 for x, y goes from 2 to infinity, f of xy dy dx. This is going to be 0 to 7, 2 to, now outside this it's going to be 0, right? So your x, so your x is non-zero only in 0 to 10, and y is non-zero only from 0 to 10. So you will start, this will be 0, you have 2 to 10, 1 by 1500 x plus 2y dy. dx dy dx. And the calculation will show you that this turns out to be 868 over 1500. All right, so this is the setup. So we found out the expected, so we worked out a problem on probability. Now another interesting aspect is, so I would like to stop with the variance. So what is a variance? So you have already computed expected value. So variance of x in this is given by, for r. So variance is the second moment. It's going to be x minus square xy dA over r2. Similarly, you can have variance of y will be the same way. Thank you for your attention.